So I just want to cover some operations that we can do with power series. These can come in handy from time to time. So the three operations that we're specifically going to discuss are multiplication, differentiation, and integration. And honestly, these probably work exactly how you might imagine them to, but let's just get into it. So let's start with series multiplication for power series. So if I have two different series, a sub n x to the n and b sub n x to the n, and they both converge absolutely for some values of x less than r, then C will be this combination of a sub naught, b sub naught, a sub 1, b sub n minus 1, all the way out to a sub n, b sub naught. So my C sub n's will be this combination of multiplying the two coefficients together. So there is this, the takeaway from this, I know this looks kind of crazy, but the takeaway from this is there is a systematic approach to multiplying out new coefficients so that you can multiply the two series together to get a new series c sub n x to the n. And this will converge absolutely for x less than r. Okay, so let's just take a look at an example of this. So I've got two different series here. All right, so I've got x to the n and then negative 1 x to the n plus 1 over n plus 1. So if I just think about expanding each of these and what that might look like. So here's the progression here. And okay, so if this is all I gave you, I think you would have actually this like systematic approach. Even though it feels very overwhelming, we could technically get the job done. So the idea is, right, I could take 1 times everything in here. And so if I were to take 1 times everything in there, I would just get this series by itself, right? So that would be that first set of multiplication. And then I could continue on and take this term now times the entirety of this series. So what would that leave me with? Well, x times x is going to give me x squared. X times x squared over 2 will give me x cubed over 2, so on and so forth. And then we can just continue this pattern, right? So I take the x squared times all this stuff, and so that'll give me this x cubed minus x to the 4th over 2 plus x to the 5th over 3, and so on and so forth. Okay, so that would probably be our first instinct anyways with multiplying, right? That's just how you multiply these things. And so from here, we just want to notice some patterns. And so this can be the tricky part when you are multiplying two series. So if I take this entire series now and I just look at what's going on. So the first thing I look at is the x. So this x is going to be the only x in this entire series, right? The terms, the exponents on the terms are only going to go up. So I can start, if I want to add all these like terms together, this whole thing's going to start with x. And then just based on what I see here, so I've got x squared, and again, the nature of how these things are going to multiply together, these are going to be the only two x squared terms. So negative x squared over 2 plus x squared will give me x squared over 2. And then now when we look at x cubed, so again, this will be the 3x cubed terms. And so if I add those together, I will end up with 5x cubed over 6. And so we can just kind of continue this pattern. So for the next one, I would get x to the 4th over 6. So we could get this done, but the question is there any clear pattern that emerges? Not really, right? And so that's okay. So the process can be a bit tedious, but it can technically be done. So, okay, that's just multiplying series together. And we just want to know that this can be done for right now. This will come back at a later point in time, and we'll revisit it later. The other thing that I want to talk about, so I've got a theorem here. So if I have some series a sub n x to the n, if this converges absolutely on, for all x less than r, and f of x is a continuous function, then a sub n f of x to the n converges absolutely on x where f of x is less than r. Okay. So this is a little bit of a warm-up for the next concept that we're going to talk about, which is term-by-term differentiation. So if I have some series c sub n times x minus a to the n, if this has some radius of convergence r, so we can define this now as a function, f of x equal to this, on this interval, okay? So to get into the term-by-term differentiation, The function f of x has derivatives of all orders inside the interval. So we can get derivatives by taking the derivative of really that kind of formula for your terms. And this is like fine to do. So again, this is like something where I think if you had no other knowledge, you'd probably just try to differentiate the formula and that would be all good. And so this is basically telling you, yes, you can do that. So for instance, let's say that I have the function 1 over 1 minus x, which I know is equal to x to the n. So we proved this in another video. So if I had this, how could I find f prime of x and f double prime of x? Okay, so I do know what f prime of x equals. It's 1 over 1 minus x squared. But also, if I wanted to differentiate the series, I would just use that power rule, right? So I'd take this n, bring it down, subtract 1. All good. And so that's how term-by-term differentiation works. If I wanted to take f double prime, so then if I take the derivative of this is going to give me 2 over 1 minus x cubed. And if I want to differentiate term by term, or if I want to differentiate just the series, so then I just take the second derivative and I can set it up this way. And so we're told that that is all good to do. Again, we're cataloging what kinds of operations we have because this will come back in another form at some other time. So we just kind of want to note this. The last thing we're going to talk about is term-by-term integration. So again, if I have another series of that form c sub n x minus a to the n, so let's suppose it converges on our interval. So if I want to integrate f of x, then I can really just do exactly what you would expect with integrating the formula for the series, so to speak. And so this is just using that power rule for antiderivatives, right? Okay, so let's take a look at this. What's interesting about this is that this can actually have strange results for different types of series. Okay, so we're going to differentiate and then integrate this, but something surprising is going to happen. So first of all, if I think about this series here, negative 1 to the n, x to the 2n plus 1 over 2n plus 1, if I just write out a few terms of that, what do I get? I get x minus x to the third over 3 plus x to the fifth over 5. So this has all, obviously, odd exponents over odd coefficients. Okay. And so if I take this and I go term by term and take the derivative, so the derivative of 1 is, or the derivative of x is 1, take the derivative here, I get minus x squared plus x to the fourth minus x to the sixth. So we can see like this really clear pattern here. Okay, so now that I see that I have this differentiation formula, the other thing that I notice about this is that this is actually something that could be rewritten. So using this formula here, this 1 minus x squared plus x to the fourth minus x to the sixth, okay, here's what's cool about this. This is a geometric series, and in this case, my ratio, my r, is negative x squared. And since it is a geometric series, we have that nice little formula, right, where I could rewrite all of this, right? What does this converge to? I can just use that geometric series formula. And so this converges to 1 over 1 plus x squared. And this is where we have this interesting turn, because now that I see that I can rewrite this as something equivalent and it is a geometric series, what happens when I integrate this? When I integrate this, so if I integrate the formula that I know that I have, this is going to give me inverse tangent of x plus c. Pretty interesting, right? So our original series was equivalent to that. And that's something that we're just going to notice for now, but we're going to add more onto that as we go through other videos. And so that means that my f of x is actually equal to inverse tangent of x plus c, and that is equal to the original series that I had. So just something interesting to notice. Okay, and I'm going to leave it at that. So I will talk to you guys in another video. Bye!